Hi all, let's continue with the concept of data hazards. In this lecture, we are going to talk about how to resolve the data hazard situations in a pipeline. So coming to the contents, we are going to discuss about different types of methods that are used to resolve the data hazard situation, such as pipeline bubbling and operand forwarding techniques. So in the previous lecture, we have already discussed about what is a data hazard and what are the different situations in which a data hazard condition occurs in a pipeline. So basically, a data hazard is nothing but it is a situation which is caused between the instructions which are being executed simultaneously in the pipeline when there is a data dependency situation between two closely spaced instructions in the pipeline. Data dependency situation here means that when one instruction it depends upon the output of the previous instruction. When we say that there is a data dependency situation between the instructions. So when those type of dependencies occurs between the instructions that are executed simultaneously in a pipeline, we call it as a data hazard situation. And we have already seen about the different types of data hazards, such as read after write, write after read, and write after write. There are three types of a data hazard situation, and we have seen them with an examples. So here we are going to discuss about how to resolve the data hazards in a pipeline. So there are several solutions that are used to resolve the data hazard situation, and some of them are pipeline bubbling or pipeline stalling method, and the second one is operand forwarding or data forwarding technique. So these two are one of the most important solutions in order to resolve the data hazard situations in a pipeline. Where the first technique, the pipeline bubbling or pipeline stalling technique, is a software approach in order to resolve the data hazard, whereas operand forwarding or a data forwarding technique is a hardware method that is used to resolve the data hazard situation. Now let us see them with an example. So coming to the first method of resolving a data hazard, pipeline bubbling. So pipeline bubbling is also known as a pipeline break or pipeline stalling. So it is one of the software methods for preventing the data hazard situation. So pipeline stalling or pipeline bubbling is nothing but you're going to delay the execution of an instruction which is caused by a dependency, or it is caused due to an inability to proceed due to a hazard situation, such as data dependency situation. So in those type of situations, you are going to delay the execution of an instruction in a pipeline. So it means that the pipeline needs to temporarily pass or stall the flow of instructions, preventing the new instructions from entering into the pipeline. So you're going to temporarily stop the execution of instructions by stalling the pipeline or bubbling the pipeline. So that is called as a pipeline bubbling or pipeline stalling technique. And whenever the instructions are fetched, the control logic that is present internally, it has to determine whether there is a hazard, there is a possibility of a hazard situation in the pipeline. If it identifies that there is a possibility of a hazard, then it has to insert the control logic itself has to insert an NOP instructions into the pipeline. So how can you implement pipeline bubbling technique in the pipeline is with the help of an NOP instruction. Since it is a software approach, by means of instructions you are going to implement the bubble using an NOP instruction. So thus, before the next instruction is executed, the previous one, which has an insufficient time to complete and prevent the hazard. So that you can, when you insert an NOP instruction into the pipeline between two dependency instructions, there will be enough amount of time for the previous instruction to complete its execution before the next instruction starts its execution, so that the dependency will be resolved. So if it is a responsibility of the entirely on the software, so that the compiler itself will insert the NOP instructions in order to obtain the correct results. And here there is also a limit on the number of NOP instructions that can be placed between any two instructions. The limit is that if the number of NOP instructions is equal to the number of stages of your pipeline, then you have to clear off all the instructions in the pipeline and proceed from the starting of the pipeline. Say for example, if you are dividing your pipeline into four stages: fetch, decode, execute and write back. Then the number of stages of your pipeline is a 4-stage pipeline. So you can place at most 4 NOP instructions between 2 instructions where there is a dependency in the pipeline. If the number of NOP instructions is greater than 4, then you have to clear off all the instructions from the pipeline, and we call it as a flushing the pipeline. So you have to completely flush the pipeline and start from the starting of the pipeline. So all the forms of stalling introduces a delay. So when you are placing NOP instructions, you are stalling the pipeline, which means there will be surely a delay in the execution of the instructions. So if you take an example, this is an instruction I1 multiplication where it is going to take the contents of R2 and R3 register, multiply, and the result is stored in R4. And similarly, I2 instruction, which is an add instruction, it uses R4, which is a destination register of this particular instruction mul. So when you place these two instructions simultaneously in a pipeline, you cannot able to get this particular operand in the decode stage of your pipeline, because until the write back stage of this particular instruction is completed, the result will not be available as an input to your second instruction. So we are going to stall the pipeline for 2 clock cycles by placing 2 NOP instructions into the pipeline. So this is called as pipeline bubbling or pipeline stalling technique, which is a software approach of dealing with data hazard situations. So coming to the advantages and disadvantages of data hazards, the advantage is when you are inserting the NOP instructions, which is a software approach done by the compiler, it leads to a simpler hardware because you are not making any uh, complications or any implementations in your hardware. It is purely a software approach. So that is an added advantage. There will not be any complexity in your hardware involved. And the disadvantage is it leads to a larger code size. Into the next type of technique that is used to resolve the data hazard situation, which is operand forwarding or a data forwarding technique. And this technique is purely the hardware based approach to resolve the data hazard situation. So if you see an example of an operand forwarding or a data forwarding technique, I have 5 instructions I1, I2, I3, I4 and I5. Consider there is an instruction I1, there are 2 instructions I1 and I2 where the instruction I2 is dependent upon the result of the previous instruction I1. So that is used as a source operand for the instruction I2. So the instruction I2 cannot move forward because until the write back stage of the instruction I1 is completed at the end of the 4th clock cycle. So at the end of the 4th clock cycle, in the operand forwarding or a data forwarding technique, what we do is rather than making the instruction I2 to wait until the 4th clock cycle, the output of the instruction I1 will be available at the end of the 3rd clock cycle in the buffer, intermediate buffer. So that is forwarded as an input to instruction execution unit of instruction I2 as an input, so that the particular data which is required by the instruction I2, which is an output of the previous instruction, is directly forwarded to the execute unit of your next stage, so that the delay can be reduced to some extent or eliminated. So this is called as operand forwarding or a data forwarding technique. So at the end of a 3rd clock cycle, the output of I1 will be available, so that is forwarded as an input to the execute phase, so that the instruction I2 can start its execution in the 4th clock cycle. Say it takes 3 clock cycles to complete. So it takes 3 clock cycles to complete, and the write back stage will take place in its clock cycle 7. So this is how you can avoid or eliminate the data dependency situation between the instructions by implementing the concept of operand forwarding or a data forwarding technique. So here the delay can be reduced or possibly eliminated if we arrange the hardware such that the result of the instruction I1 is forwarded directly to the use in the step E2. So from E1 it is directly forwarded to E2 step, which is known as data forwarding or operand forwarding technique. So here you have to make your changes in your hardware in such a way that it implements the concept of operand forwarding, and there is a data dependency situation. So the data forwarding mechanism works as follows. So the forwarding here is implemented by feeding back the output of your previous instruction into the next stage of your pipeline. Next stages of your pipeline as soon as the output of that particular instruction is available. So if you look at your hardware, so from your fetch stage, decode stage, the instruction will be placed into the buffer and give it as an input to the execute unit. From the execute unit, the result will be copied into this intermediate buffer and giving it as an input to your register file or write back stage. So whenever there is a data dependency, say for instruction I1 as executed and the result is available in this particular buffer. So for I2, when there is a dependency, rather than forwarding it to the next stage, that will also take place. But before that, it will be the result which is already available. It will be given as an input to the execute unit for the next instruction I2. So this technique is called as operand forwarding technique, and we call this particular path as a forwarding path. So this is how the data forwarding or operand forwarding techniques are used. Thank you.